If you're grinding through another traditional engineering textbook right now, you might be learning the wrong version of engineering. Everyone tells you the same thing. Get the degree, master the equations, learn CAD, pass the exams, get an internship, and somehow a great career appears on the other side. But here's what almost no one is saying out loud. In 2026, the engineers getting ahead aren't always the ones who can solve the longest equation by hand. They're some of the ones who can use AI tools, simulations, automation, data, and systems thinking to solve real-world problems faster than everyone else. Traditional engineering isn't dead, but the traditional path is getting crowded, slow, and way less differentiated. And while most students are still trying to become good at engineering the old way, a new category of careers is opening up. Careers where you're building systems, automating workflows, using AI to test ideas faster, and connecting hardware, software, data, and business problems together. So in this video, I'll break down exactly what I'd learn instead of traditional engineering if I were starting over in 2026. So here's the lie that keeps a lot of future engineers stuck. It's, if I just become technically strong enough, companies will automatically want me. That sounds logical, but it's incomplete. Companies don't hire engineers just because they know formulas. They hire engineers to reduce costs, improve systems, design better products, prevent failures, and solve expensive problems. That's the part most students miss. They spend years asking, what software should I learn? But the better question is, what problems can I solve that companies actually care about? The opportunity isn't in being the person who just follows instructions. It's in becoming the person who can turn engineering knowledge into real-world impact. So traditional engineering is not dying. It's splitting. Engineering is not going away. We still need civil, mechanical, electrical, aerospace, and every other serious discipline. Bridges still need to stand. Aircraft still need to fly. But the role of engineer is changing. The old version was mostly about calculation, documentation, and discipline-specific expertise. The new version is about combining engineering fundamentals with AI, software, data, simulation, automation, and communication. If your entire identity is, I know the formulas, AI is going to make that less impressive. But if your identity is, I can use every tool available to design, test, validate, explain, and improve a real system, then AI makes you more valuable. AI is not replacing great engineers. It's exposing average ones. So let's talk about the modern engineering value ladder. So level 1 of this ladder is the formula follower. At level 1, you can solve textbook problems, complete assignments, follow tutorials, make a basic CAD model. That's where everyone starts, but also where most people get stuck. If all you can do is follow instructions, you are replaceable. A lot of engineering portfolios look like this. A student designs a part in CAD, runs a basic stress simulation, shows a screenshot, and says, here is my project. But what problem did it solve? What trade-off did it make? If you can't answer that, it's not an engineering project. It's just a software demo. Let's move on to level 2, the AI-assisted builder. At level 2, you're still using engineering fundamentals, but using modern tools to move faster. You can use AI to brainstorm concepts, write Python scripts to automate calculations, build and interpret simulations, prototype with microcontrollers, and use CAD and analysis tools to answer real engineering questions. You're not just learning tools, you're building workflows. Instead of designing a bracket, you compare 5 design options based on weight, cost, strength, and manufacturability. Instead of saying, here is my CAD model, you say, here is the problem, here were the constraints, here's the trade-off, and here is my recommendation. That is a completely different level of value. Let's move up to level 3 of the ladder, which is the system driver. So level 3 is where the real career leverage is. You're no longer solving isolated problems. You're influencing decisions. You understand how mechanical, electrical, software, data, cost, safety, reliability, and business needs to connect. You can walk into a meeting and say, here are 3 options. Option 1 is cheapest, but has the highest maintenance risk. Option 3 gives us the best balance of performance, cost, and reliability. Here's the data, here are the assumptions, and here's what I recommend. That's what companies pay for, not just technical output, technical judgment. And most people never reach this level because they spend all their time trying to get better at tools instead of better at thinking. So let's talk about some important skills that you'll need. So skill 1, AI-assisted engineering workflows. So not just prompt engineering. That's too shallow. I'm talking about using AI as a serious engineering co-pilot, summarizing technical standards, generating test plans, debugging code, comparing design concepts, and speeding up repetitive work. But here's the key. Learn how to verify everything. In engineering, being confidently wrong is dangerous. You need to understand the fundamentals well enough to catch bad assumptions. The beginner says, AI gave me the answer. The professional says, AI gave me a starting point. I validated it against first principles, constraints, data, and standards. That is the mindset. Skill number 2, Python, data, and automation. This might be the highest ROI skill for engineering students because so much engineering work is repetitive. Calculations, reports, data cleaning, sensor logs, design comparisons. If you can automate boring work, you instantly become more valuable. You don't need to become a full software engineer, but you should be dangerous with Python. Import a CSV, clean it, analyze it, visualize it, explain what the data means, automate calculations, build simple scripts that save hours of manual work. Modern engineering is becoming more data-driven every year. Mechanical systems, buildings, factories, vehicles, energy systems, they all create data. The engineer who can understand the physical system and analyze the data from it has a massive advantage. That person sits between the real world and the digital world, and that is a very powerful place to be. Skill number 3, simulation, digital twins, and validation. Most beginners treat simulation like a screenshot generator. They make a model, click run, get a colorful stress plot, and call it engineering. That's not enough. You need to understand what the simulation is assuming. What boundary conditions did you use? Does the result make physical sense? How would you validate it with a real test? That last question is everything. Simulation without validation is just expensive guessing. Learn FEA, CFD, system modeling, BIM, or digital twin concepts depending on your field. But the mindset is always the same. Model the system, test the assumptions, validate with data, communicate the decision. Skill number 4, systems thinking and product judgment. This is the skill almost nobody talks about, but it separates average engineers from great ones. A traditional engineering student asks, can I solve this technical problem? A systems thinker asks, should this problem be solved this way at all? Real engineering is full of trade-offs. Performance versus cost, strength versus weight, speed versus safety, innovation versus reliability. The best engineers don't optimize one variable. They understand the whole system. Maybe you can design a part that's 20% stronger, but it costs twice as much to manufacture, requires a rare material, and makes maintenance harder. Is that actually better? That is systems thinking. This is also where communication becomes a technical skill. A confusing engineer gets ignored. A clear engineer drives decisions. Skill number 5, sustainability, energy, and real-world constraints. Not because it sounds trendy, because the physical world is being rebuilt around energy, infrastructure, electrification, manufacturing efficiency, and resource constraints. The opportunity isn't in memorizing buzzwords, it's in understanding the actual systems. How much energy does this process use? Can we redesign this part to use less material? Can we reduce downtime? Can we make the product easier to repair or recycle? Sustainability is not about good intentions. It's about physics, economics, design, and trade-offs. Connect those things and you'll be useful in almost any industry. So here are some things that I would stop over-focusing on. I would not spend all my time trying to perfect hand calculations that software can do faster. I would not build a portfolio full of random CAD models with no problem behind them. I would not learn 10 tools at a surface level just to put them on my resume. And I definitely would not assume a degree alone is enough. Instead, I'd build proof. Proof that I can solve problems, use modern tools, communicate, and think in systems. So here's the portfolio that I would build. Not 10 projects, 3, but each one serious. Project 1 would be an AI-assisted design project. Take a real system, redesign it under constraints, compare multiple options using CAD and simulations, and explain the trade-offs. Project 2, a data and automation project. Use real-world sensor or public data, analyze it with Python, and turn it into an engineering recommendation. Project 3, a systems project. Take a bigger problem like reducing energy use or improving a manufacturing process and show the full decision-making process. Problem, constraints, options, data, trade-offs, recommendation. That portfolio will instantly stand out because it shows how you think. And in 2026, how you think matters more than how many tools you claim to know. So here's the roadmap. 1. Learn engineering fundamentals well enough to not be dangerous. Math, physics, mechanics, whatever applies to your discipline. Learn Python and data analysis, practical automation, data cleaning, visualization, and simple modeling. Learn one serious engineering toolchain to your discipline. Learn AI-assisted workflows, research, documentation, coding, design reviews, troubleshooting. Learn communication, technical writing, one-slide summaries, clear visuals, decision memos. Build decision-driven projects that prove you can combine all of it. The engineering world is changing fast. The people who adapt will have a massive advantage. The people who keep acting like it's still 2010 will wonder why their degree isn't creating the opportunities they expected. Traditional engineering knowledge still matters, but by itself, it's no longer enough. The real opportunity is combining engineering fundamentals with AI, automation, simulation, data, systems thinking, and communication. Not someone who just solves equations. Someone who builds, validates, improves, and explains systems that matter. That choice is yours.